Okay, welcome to lecture 25. So we're still on unit 3 here, covering the Laplace transform. And so today we're going to be solving initial value problems using the Laplace transform. So we're going to be covering two different types of initial value problems in this lecture. The first being equations with constant coefficients. So this is a case that we've seen previously, right? We've solved equations with constant coefficients using a variety of ways, both homogeneous and non-homogeneous cases. But we haven't really solved equations with polynomial coefficients, except in the specific case of the Cauchy-Euler equations. Okay, but if you get an ODE which is not in the form of the Cauchy-Euler equations, then we actually haven't learned how to solve it. So we're going to do that today using the Laplace transform. So just recall a couple of properties of the Laplace transform from an earlier class. So the Laplace transform of the first derivative of a function f of t, is equal to s times the Laplace transform of f minus, this is sort of like the initial condition, right? When t is equal to 0, what does the lowercase f equal? And then there's a similar form for the second derivative of f. Okay, so we can take the Laplace transform of f itself or its derivatives. So these properties make it possible to solve an initial value problem directly. Okay, so previously what we've done is we've found the general solution to the ODE and then used the initial conditions to find the particular solution to the initial value problem. Okay, but the really nice thing about this Laplace transform method, or at least one of the really nice things, is that the initial conditions are built into the Laplace transform. Okay, because so the initial condition on f appears in both of these terms here, and the initial condition on f prime also appears in this Laplace transform of the second derivative. Okay, so this is a really nice property of the Laplace transform, is that we can integrate the initial conditions into the Laplace transform method. We don't have to do it separately at the end. But a second really nice property of the Laplace transform is that it works for both homogeneous and non-homogeneous ODEs without any real additional difficulty. And so this is nice because, you know, previously we had to find the general solution to a non-homogeneous ODE. We first had to find the complementary solution, and then secondly find a particular solution, and that could be quite a lot of work. Okay, but the Laplace transform, it works for both homogeneous and non-homogeneous ODEs in exactly the same way, in fact. So the basic idea is that we take the Laplace transform of both sides of the ODE and then use the initial conditions and the Laplace transform properties to obtain an algebraic equation for the Laplace transform of the solution. Okay, so in the case of constant coefficients, what we're going to find is that when we take the Laplace transform of both sides, we're going to have an algebraic equation, which of course we can just solve for y of s. And then of course, once we've solved for the solution to the algebraic equation in the s variable, we have to take the inverse Laplace transform of that solution to obtain the solution in the original variable t, which we often use t. Okay, so let's look at an example here. So here we have a second order linear non-homogeneous ODE with constant coefficients. Okay, and in fact it's an initial value problem because we have our two initial conditions here as well. So we could solve this ODE using the methods that we learnt in Unit 2. So for example, we'd find the solution to the associated homogeneous problem by solving y double prime plus 5y prime minus 6y equals 0. And then we could find, let's say, use the method of undetermined coefficients to find a particular solution in the form of exponential of t. Okay, so we could do that using the methods of Unit 2, but we could also solve this problem using the Laplace transform method. Okay, and it has some advantages. So the first thing we'll do is we'll take the Laplace transform of all terms on both sides of the equation. So the Laplace transform of the second derivative of a function, you can see this Laplace transform property in the top right is equal to s squared times the Laplace transform of y minus s times this first initial condition minus the second initial condition. And of course, these are just numbers. So the first initial condition, when t equals 0, y is equal to -1. And then the second is when t equals 0, y prime is equal to 9. So we can use those numbers in this equation to find that the Laplace transform of y double prime is equal to s squared times y of s plus s minus 9. We can do the same thing with the first derivative of y, so s times y of s minus the first initial condition, which is -1. So minus -1 is +1. And then finally we can, next we can take the Laplace transform of y itself, which is just y of s. And the Laplace transform of e to the t is 1 over s minus 1. So this is straight from the Laplace transform properties that we learned earlier in this unit. So we can use these terms in the ODE, okay, and we get s squared y plus s minus 9, so that was our Laplace transform of y double prime, the second derivative of y. Then we have the 5 times the Laplace transform of y prime, so 5 times s times y plus 1. Then we have minus 6 times the Laplace transform of y, minus 6 times y. And then 21 times the Laplace transform of the exponential of t, this term here. Okay, we can rearrange now to make y the subject of this equation. Okay, so this is going to be an algebraic equation. So I have some factors of y here, some common factors of y. So I have an s squared times y here. I have a plus 5s times y here, and I have a minus 6 times y here. All the other terms I'm going to take to the right hand side of the equation, like so. Here are my terms that are multiplied by y. And then this term on the right hand side here, I want to write this over a common factor. So I'm going to cross multiply 21 over s minus 1, take away s plus 4, 9 minus 5 is 4, s plus 4 over 1. So those two fractions I'm going to cross multiply to find a single fraction. Okay, and of course I can simplify this numerator here as well. I can then divide through by s squared plus 5s minus 6 to get y as the lone subject of the equation here. Okay, but this s squared plus 5s minus 6 term here, this term can be written as s minus 1 times s plus 6, right? So this this fraction here, this is a solution in y of s, the variable s, okay? But now we want to find the solution y of t. So we want to take the inverse Laplace transform of y of s, okay? And that will give us y of t. But notice here that y of s is a ratio of two polynomials, and the degree of the polynomial on the bottom, the denominator, is 3, which is greater than the quadratic that we have on the numerator. So therefore we can use partial fraction decomposition to solve this problem. We have one repeated linear factor s minus 1 and one non-repeated linear factor s plus 6. So therefore we can write y, which is this ratio of these two polynomials, as a over s plus 6 plus b over s minus 1 plus c over s minus 1 squared. What we're going to do then is multiply both sides of the equation by this denominator on the left hand side. So s minus 1 squared times s plus 6. On the left hand side we get left with negative s squared plus 5s plus 17. And on the right hand side, well, you can see some terms cancel. I'm going to let s equals 1 here, because if I do that, then this a term I get 1 minus 1, which is 0, so this term disappears. Similarly here in the b term I get 1 minus 1 is 0, so this term disappears. The c term, I get 1 plus 6 is 7, so I get 7c. Over on the left-hand side, I get negative 1 squared is negative 1, plus 5 plus 17 is 21. So I end up that c is equal to 3. Similarly, I can do the same thing. I can let s equal negative 6, because that is going to cancel out this b term here and this c term, and I can find quite simply that a is equal to negative 1. And then to find the other unknown b, I'm going to look at the s squared terms. Okay, so on the left hand side I have negative 1 s squared term. On the right hand side I have 1a plus 1b s squared terms here. So clearly I can see that b equals 0, and I can write my solution y of s like so. Negative 1, so this is a, times 1 over s plus 6, plus 3, which is c, times 1 over s minus 1 squared. So now to find the solution y in terms of the original variable t, I have to take the inverse Laplace transform of capital Y, which is in terms of the variable s, and because the Laplace transform and the inverse Laplace transform are linear functions, linear operators, then I can split this up and write this as negative the inverse Laplace transform of 1 over s plus 6, plus 3 times the inverse Laplace transform of 1 over s minus 1 squared. Okay, so the first term here is quite straightforward, because if you recall, the Laplace transform of e to the at is equal to 1 over s minus a. So if a is equal to negative 6, then exponential of negative 6t is equal to 1 over s plus 6. So this first term here is just simply going to be negative the exponential of negative 6t. The second term here is slightly more challenging. But first let's imagine if we did not have this negative 1 here, if it was just 1 over s squared, then I would know that the inverse transform of that would be t, because the Laplace transform of t is equal to 1 over s squared. Okay, so this is going to look something like t here, or 3 times t here. But because I have this negative 1, I can use the properties of the Laplace transform, specifically the first shift theorem, or the first translation theorem, as it's sometimes called, to get this negative 1. So what I'm going to do, if I took the Laplace transform of t times e to the t, then I would get 1 over s minus 1 all squared. Okay, so therefore y of t, so y in the original variable t, is equal to negative 6 exponential of negative 6t plus 3 times t times e to the t. And you can check that this solution matches the one that you find using the method of undetermined coefficients from Unit 2. Okay, so the Laplace transform method works well for any form of the right-hand side, which is an advantage over the method of undetermined coefficients, as long as we can find the Laplace transform of the non-homogeneous term, or the right-hand side of the ODE, and as long as we can find the inverse Laplace transform of the solution y of s. Okay, so there is some advantage to using this Laplace transform method. The other being that we solve everything together, right? The Laplace transform method automatically accounts for the initial conditions when we take the Laplace transform of the two derivative terms, and it also automatically accounts for the non-homogeneous terms. Okay, so there are some advantages here. The other advantage is that we can solve equations that we have not been able to solve before, which we're going to move on to now. So far in this class, we have not solved any initial value problems with ODEs that have polynomial coefficients. Okay, we have solved the Cauchy-Euler equations. So they were a very specific type of polynomial coefficient ODE. But in general, we have not learned how to solve second order linear ODEs with polynomial coefficients. So let's recall the following property of the Laplace transform. Okay, so the Laplace transform of t to the power of n times some function of t equals negative 1 to the power of n times the nth derivative with respect to s of f of s, which of course is the Laplace transform of f of t. Okay, so let's look at the specific case when n equals 1. So when n equals 1 and our function f equals the derivative of y prime, then we have the Laplace transform of t times y prime is equal to negative 1 to the power of 1, so negative 1 to the power of 1, times the first derivative of f of s. So negative 1 times the first derivative of the Laplace transform of y prime. But the Laplace transform of y prime is just simply s times Laplace transform of f minus this first initial condition. So we end up with negative 1 times the derivative with respect to s of s times y minus this initial condition. But this initial condition, y is 0, is just a constant. So when we take the derivative, d by ds, of this constant, we get 0. Okay, so the derivative of a constant is 0. The derivative of this term here, s times y, well, we must remember that y itself is a function of s. So we're going to have to use the product rule here. So therefore, the Laplace transform of t times the derivative of y is equal to negative s times y prime minus y. So now we don't actually have an algebraic equation here, we have an ODE here. So t times the y prime gives us an ODE, or at least a derivative term. If we do the same thing for the second derivative of y, n equals 1 and f equals y double prime, then, and we take its Laplace transform, then we get negative derivative of s squared times y. So again, something we'll have to use the product rule on. Minus s times y of 0, so the first initial condition. This is going to be just, when I take its derivative, this is just going to be equal to y naught, right? Because this s will just become 1 when I take its derivative. Minus the second derivative, or the second initial condition here, sorry. And again, that's a constant, so when I take its derivative, I get 0 here. Okay. So that's what I said. I already said those things. Okay, so this is equal to, from the product rule, negative s squared times y prime minus 2s times y plus y 0. So product rule, first two terms of the product rule, and the last term here is the y0 term. Okay, good. So, if the coefficients of the ODE are, well, let's say constant coefficients, then previously we got an algebraic equation, but now if the coefficients of the ODE are polynomials of degree 1, then the differential equation for y of s becomes a simple linear first order ODE. So we've taken our second order ODE with non-constant coefficients, and we've turned it into a first order ODE, which we can solve using any of the methods in Unit 1. So again, if the coefficients of the ODE are constants, we get an algebraic equation in y of s, but if the coefficients of the ODE are first order polynomials, then we get a first order ODE in y of s. We also have a property here that we need to remember, that if f of t has a Laplace transform, or in other words, it's piecewise continuous and of exponential order, then we have this property that the limit as s goes to infinity of f of s is equal to 0. And so we're going to use this property to solve some initial value problems. So let's look at an example here. So we have an initial value problem here. Well, the initial conditions are nice and easy. Y of 0 equals 0. Y prime of 0 equals 0. Okay, and the ODE associated with this initial value problem is y prime prime plus t of y. So here's this polynomial times y prime minus 2y equals some non-homogeneous term equals 2 here. So the thing that's different and that we have not been able to solve using any other method we've learned in this class is that our y prime term here is multiplied by this polynomial t. To solve this, we're going to use the Laplace transform method and take the Laplace transform of each term. So the Laplace transform of y double prime is equal to s squared times y. These two initial conditions are both 0, so we just get s squared times y. The Laplace transform of t times y prime, well, we just learned that that was equal to negative s times y prime of s minus y of s. We take the Laplace transform of 2y, we just get 2 times y of s. And if we take the Laplace transform of 2, we just get 2 over s. So now we use these terms in the ODE. Okay, so the y double prime term here is in red, minus t times y prime. So this minus s y prime minus y. This is term in green. Minus 2 times y is minus 2 times y of s, and the 2 is 2 over s. So we've just taken these four terms and used them in the ODE. Okay, we can simplify or rearrange this equation to write this in the form of a first order linear ODE. So I can already see that this first order linear ODE is not separable. So s here is the independent variable. This capital Y of s is the dependent variable. It's not separable, but it is in the right form to solve using an integrating factor. Okay, so if you recall that mu is equal to the exponential of the integral of the thing that's multiplying this y. Okay, so this term here. So I can simplify this fraction here as 3 over s minus s. Okay, and then if I integrate that, I'm obviously going to get a logarithm term here. So 3 times the log of s, or let's just say the logarithm of s cubed, minus s squared over 2. Okay, then I can use the properties of the exponential to write this as the product of two exponentials. So the exponential of the log of s cubed multiplied by the exponential of negative s squared over 2. The exponential of log of s cubed is just s cubed. So therefore mu is equal to s cubed times the exponential of negative s squared over 2. Okay, so then I can immediately solve for y. So y is equal to 1 over mu, so 1 over s cubed e to the negative s squared over 2, times the integral of the right hand side, negative 2 over s squared, times mu again, integrating with respect to ds. Well, obviously here we have an s cubed over s squared, which simplifies to just s. And this integral here turns out to be quite easy, in fact, because I am multiplying the exponential. Well, let's just say if I differentiated this exponential here, I would get this exponential back multiplied by negative 2s over 2. So I get multiplied by negative s. Okay, so that integral is pretty straightforward. When you first look at this integral, in fact, you might think, well, I have to use integration by parts. And in fact, it would actually work using integration by parts, but I could already see that the second term here, if I differentiated it, I would get basically exactly this form here. So that's, I guess, a shortcut if you can see it. So this is my solution in terms of y. Well, I can simplify this a little bit because I can bring this exponential inside both of these terms here. That way this exponential term cancels in this first term, and I get left with y is equal to 2 over s cubed plus a second term involving some integration constant c0 here. Okay, I don't really want this integration constant c0 in my solution though. So how can I find this integration constant? Well, I've already used the initial conditions when we calculated the Laplace transform of y double prime and y prime. Okay, so I shouldn't really use them again if I can help it. But I can use the fact that the limit of this thing y of s when s goes to infinity should be equal to 0. Okay, this was just a property of if y had a Laplace transform, it had to satisfy this property. So let's look at these terms here. As s goes to infinity, 2 over s cubed goes to 0, so that's good. The second term here though, as s goes to infinity, we have some constant divided by s cubed, which is going to infinity, times exponential of negative s squared over 2. So this exponential is going to 0. So I have a 1 over infinity times 0 situation here. Okay, but the exponential is always going to go to 0 faster than the s is going to blow up to infinity. So in fact, the exponential is going to dominate this this fraction here. You can check this using L'Hopital's rule, or any other way you can think of, but exponential is decaying to 0 faster than s cubed is increasing to infinity. So in fact what we get is a 1 over 0 situation here, and so this second term here is not going to 0 as s goes to infinity. This second term is going to infinity. Therefore, if I want y of s to go to 0 as s goes to infinity, my integration constant c0 has to be 0. Therefore, y is equal to 2 over s cubed, and which I can take the inverse Laplace transform of, right? And so this is just going to be t squared. So, well, again, this just comes from knowing my Laplace transforms or looking at the Laplace transform table. So make sure you're comfortable with that. So I guess in summary, what we've learned today is that this Laplace transform method is really useful because A, it automatically accounts for the initial conditions in initial value problems. B, it is possible, it automatically, I guess, accounts for all the non-homogeneous term. I don't have to split this up into a complementary solution plus a particular solution. It solves it all in one piece. If I have a initial value problem with a polynomial coefficient, it also solves this type of initial value problem, which we haven't been able to solve using any other method that we've learned so far in this class. So in summary, the Laplace transform method is a really powerful method, one that we have to know, and one that is really practically used in a lot of mathematical modeling, solving differential equations. Okay, I'll see you in the next class.